Okay, let's start maybe, okay?
Sure.
So today, Dr. Turowski will talk about one kind of a dynamic network, duplication divergence, that has a lot of applications. A silly one is when you copy, when you write a paper and you have to put reference, you basically copy from the other paper, delete, add something. A good application is protein-protein network in biology. And the other problem is compression. And this leads to something interesting in graph symmetry. So Krzysztof, please start.
Okay, thank you. Today I'll be talking to, this is the first of two talks about duplication divergence model and the results that we, with Wojtek, Alan Fries, and Philippe Jacquet, and many more, we did around it. And I decided to split the whole presentation of our results into two parts. Today it will be boring, long, tedious algebra, and next week it will be more, let's say, it should be more practical oriented, but in a specific sense of the term. So it will be rather concerned with problems like model fitting. So whenever we have some networks, we would like to fit some model to it, or with guessing the proper temporal ordering within the network. Anyway, well, here we have first get to know what are the dynamic networks and what is the duplication divergence model. And as Wojtek mentioned, it is quite popular model that can be used to express certain properties of such various networks as some social networks, biological networks. Here we have even some brain networks, I suppose. And they all exhibit certain properties that actually turned out to be captured quite nicely by this model. What are these properties, and what is the main idea behind the study of dynamic networks? So we want to look at the complex system, and here the graph, which is dynamic in the sense that it has certain rules that describe the time evolution of this network. Here we have interacting entities. The entities, of course, are represented by vertices, and their interactions are represented by edges. And the whole spatial structure and the pattern of interactions changes over time. As the time progresses, we execute certain rules. These rules are typically probabilistic in nature, and we would like to study the behavior of the whole system over a certain span of time. Okay, so what we can study about such networks? First, we can study what exactly the underlying process is. So we can try to check which models do fit certain real-world networks, and under which assumptions, and which parameters of which sets of parameters look the most promising to describe the network evolution. Here I wrote that sparsely sampled system state, because usually we do not have a complete information, for example, about the evolution of the network. We have only certain snapshots describing our incomplete knowledge about the system. The second is that suppose that we have a certain plausible model, then it can become an object of an independent interest. We can study its properties. For example, we can study what are the degrees of vertices which arrive, what are the such network parameters as clustering coefficient, so how dense is the graph or how clustered is the graph. We can study degree distribution. And of course, since dynamic networks are used quite often to describe data such as I mentioned, social networks, biological networks, we often want, since these networks are within a number of tens of thousands, hundreds of thousands, millions, we want to store them efficiently. So under the assumption that a graph comes from a certain model, we would like to be able to determine the amount of bits that we need to describe certain dynamic networks. And of course, the more the algorithm is suited for the particular model, which in turn fits the graph, the better. Okay, so these are three broad ideas, and today I'll be mostly talking about the second one, and next week I'll be talking about the first and third one. So today it's assuming that we have this model that I will describe soon. What are its properties? And we'll basically concentrate on degree distribution and its various properties. Okay, so let's start with a very simple model that was called pure duplication model in the literature. And it is defined by a very simple rule. So we start with a certain graph on T0 vertices. Usually it is assumed that it is a small clique. And we add vertices one by one in the following way. Next vertex comes. It chooses uniformly at random one existing vertex. And so, okay, I described here the other way around, but new vertex arrives. It is chosen as a child of another vertex. And then we pick every neighbor of the parent, and we flip a coin with probability P. And if it turns heads, then we add an edge between our new vertex and the neighbor of parent. Note that in this model, there is no connection between a new vertex and its parent. So a new vertex is, with large probability, can be in distance 2 to its father. It can be also an isolated vertex if all the flips come as tails, but it can never be adjacent to its parent. And this is the basic model. And for simplicity, we view the vertex set of the graph as a set of natural numbers from 1 to t. Next vertex comes. It gets a label 1 higher, and then we repeat this process until we reach the desired number of vertices. Okay, so a small illustration of this process. Suppose that we start from this graph on 6 vertices. Then we add a new vertex, V1, and let's suppose that it chose U2 as its parent. So we flip a coin for each 3 neighbors of U2, that is U1, U3, and U6. And it turns that it was head in all 3 cases. So we make V1 adjacent to all 3 of these vertices. Next, we repeat this process and we create a new vertex V2, which is a child of U1. And again, we throw our coin twice. Here we have one's heads, one's tails. So we make V2 a neighbor of U2, but we do not make V2 a neighbor of V1, despite the fact that U1 is a neighbor of V1. Okay, and we repeat this process. V3. Here, it is ambiguous that both U2 and V1 could be parents of V3. Of course, depending which vertex we chose as its parent, then we have to perform different number of coin tosses. And there are different possibilities, so different probabilities to obtain exactly this structure of neighborhood that V3 has. So in fact, not only the ordering, the temporal ordering of the vertices matters, but also exactly which vertex was chosen as the parent of a particular vertex. Because in some cases we have larger probabilities, and in some cases we have smaller. Okay, so this was pure duplication model, and it had certain problems. For example, if a vertex was isolated, in pure duplication model, it stays isolated forever. So this model, as it can be simply proved, it results eventually in the case that quite a large fraction of vertices, in fact, as a number of vertices goes to infinity, almost all vertices are isolated. So it doesn't seem like a plausible model for the many networks that we are considering. But fortunately, we can fix it using another simple rule. And here are the two examples of such a rule. For example, Chung and Lu proposed a model in which we have additional coin toss to connect vertex U with its parent V at every step. And we toss a coin. This, especially when we fix Q equals 1, then it guarantees that there is some spanning tree in the graph, that this graph is connected. So this is fine. Still, it does not make the graph connected enough for certain purposes. So there was another modification proposed by Pastor Satoras. And this, in comparison to Chung and Lu are two different people, and Pastor Satoras is a one man, actually, with two surnames. And he with his collaborators, they proposed a certain model which would be described as following. We perform every duplication step as it was. Then we perform additional operations. So we pick all non-neighbors of a parent of a vertex, and we flip a coin with some small probability. That is probability, some constant R divided by number of vertices which are currently in the graph. And we toss a coin for each non-neighbor of parent. And if it heads, so with this, if it turns head with this probability, then we join new vertex with some non-neighbors. And this allows another round of divergence. So not only new vertex isn't connected to some neighbors of its parent, but it also can be connected to some non-neighbors of its parent. And as you suppose, on average, around R additional edges appear at each step due to this modification. And the latter model turns out to be very well suited to for many types of biological networks. So, for example, for protein networks, which are probably our basic benchmark in all our usages. And this duplication model, of course, this is actually for the Pastor Satoras model, because it has two parameters, but the conclusions also can be found for these different type of models. Duplication divergence model has very interesting properties. So first, it has a large number of symmetries. If you look, that unless the parameter R with parameter P are very large, here, I guess here are graphs generated from this model on 2000 vertices, if I remember correctly. And if we take such vertices, and if we generate them, they have a very large number of symmetries. In fact, the larger the graph, the number of symmetries grows, and is one of our hypotheses that actually these graphs for very large set of parameters P and R are symmetric. So it's hard to generate a asymmetric graph when the number of vertices goes to infinity. But it is different from many other. For example, if you heard about Erdős-Rényi random graph model, it was proved back by Erdos and Renyi in the 60s that this model generates almost surely asymmetric graphs, or maybe it was proven somewhat later. Anyway, it was proven that unless P is very close to 0 or P is very close to 1, the generated graphs are asymmetric. Similar with preferential attachment or Barabashi-Albert model, then this model also very often generates asymmetric graphs with no symmetries in it. And on the other hand, we know that, for example, biological networks are very symmetric. So this model gains a very large advantage over these two models in terms of fitting model to the real world data. Second property, which is quite an obstacle for a theoretical analysis, is this non-equi-probable permutations. I already mentioned that choice of parents matters, but also if we have a graph, then it matters in which order vertices arrived. And if we swap some vertices, it may radically decrease the probability of generating such a graph, even though the structure is the same. And another property that is important is the power law behavior of degree distribution. And you may probably heard of power law behavior as an important phenomena that can be observed for many real-world networks. So it is also known by name scale-free property. But it gained interest also in graph theoretic community. And if the model exhibits under certain assumptions power law behavior, then this also adds to its plausibility as a potential fit to the real world networks. Okay, and if we look back from the 70s, we can find ideas, and it's quite natural to view biological networks as driven by some kind of evolution mechanism. And this evolution can be seen as a way, as a variant of duplication and divergence mechanism. So whenever, for example, new protein arrives, it can be seen as an imperfect copy. So some duplication, some divergence from another already existing protein in the network. And whenever we describe protein-protein interaction, this new protein interacts with, we suppose, majority of the proteins that the old protein, its parent, was interacting. And it also exhibits some novel way of functioning. And it was already in the 70s, this hypothesis was quite loose, even way before this model was formalized. Okay, but starting with 2000, when this model came under a scrutiny of graph theoretical community, there was an analysis which was very crude, imperfect, that conjecture. So they claim they proved, but it was rather a strong conjecture and hand-waving proof than proof in formal sense, that indeed this model can generate power law networks with scale parameter between 2 and 3, which again was very big advantage over other types of models, because, for example, biological networks are supposed to have this scale parameter exactly somewhere between 2 and 3. And there are quite a few studies that try to empirically fit different types of models with different types of real-world networks, for example, by matching some small structures, triangles, open triangles, some small subgraphs, average degree. We did some work, which I'll be talking probably next week, about automorphisms. And it turns out that if we try to find parameters for these models, and then try to generate graphs which could exhibit all these values, so number of triangles, number of automorphisms, close to what we expect from the real-world networks, then this model performs surprisingly good, and it is quite a unanimous opinion that it outperforms all other models. Okay, but what about the particular properties? So let's start with very simple property, that is average degree and degree of a fixed vertex. Okay, one thing which is probably clear to you by now, that it's if we have a random graph model, then we can see it as inducing some probability distribution over all graphs on a fixed number of vertices. And then we can define random variables as we do it with in probabilistic calculus all the time. Here, I would denote by degree T of S. It would be the degree of vertex with number S, that is coming as the S vertex, in graph GT, which was generated from this model. Of course, this variable is stochastic, and we can analyze its statistics as with any stochastic variable. Clearly, it will be needed later, but this variable is closely related to the maximum degree, for one, serving as a lower bound. And again, if we would like, if we want to prove the probability of a lower bound, so probability that degree is greater than some fixed value k, then we can bound this probability by summing over all vertices that their degree are at least equal to k. Okay. First, what we did, we did some simulations, and it turned out that both degree of a fixed vertex S and maximum degree should be concentrated around some value. So when t grows to infinity, the distribution was thinner and thinner. So we were expecting that eventually it would, maybe if not converge to some value, that it'll be distributed within a small interval around some value. And we would like to confirm this finding by proving theorems about the behavior of fixed vertex and the behavior of maximum degree with high probability. Okay, but to do it, we had to start with expected value of the degree of vertex S. And here we have a very simple recurrence straight from the definition. So if we want to compute the expected degree, we have two cases. Either S at time t+1 becomes the parent, is included in the neighborhood of the parent. And of course, it is proportional to the degree of vertex S in the previous iteration. And then with probability P, we add an additional edge. And this is the first case in which degree of a vertex S can increase by 1. And the second event is that it does not belong to the neighborhood of parent of the newest vertex, but still we add a vertex with probability R over T. In these two cases, the new degree is the old degree +1. And of course, in all other cases, degree remains the same. Thus, if we compute the expected value of degree t+1 conditioned on given degree on graph at the moment t, we get this simple recurrence. Okay, but then we can iterate such recurrence. And but one other thing. So we have this recurrence, and we have a function at time t+1 dependent on the same function only at time t in a linear fashion. Then This we can repeat over and over and over until we go to the degree of vertex S at time S. And here we have to consider what is the behavior of the newest vertex. Now, the newest vertex would be can be found from the following analysis, that if new vertex comes, then of course it has it draws some vertex as its parent. It adds some edges with probability P, and then it adds some edges with probability R over T. So we have two binomial processes, and the definition of the stochastic variable is just a sum of two binomial variables. Therefore, if we apply expectation operator, then we can find straight from definition that we can reduce it to a linear function of something which is an average degree. That is, we take all the vertices in the graph, we sum them, and we divide them by the number of current vertices in the graph, and we will denote it by D of G. Okay, so we need to get the average degree defined as following, and we also would like to find its recurrence. Here, it's much easier. Here, by definition, to find an expected value of average degree at time t+1, we go straight from definition. We use the fact that we can take out, so the only new edges that appear, there are just the edges coming from vertex t+1, because we do not touch anything outside vertex t+1. Of course, ×2 because 2 endpoints, and by simple algebra, we can arrive at the following recurrence. Okay, and again, notice that we found some recurrence in the form that some property at time t+1 is a linear function of some property at time t. Okay, so we have some general recurrences and for Markov processes, and we have certain properties that these functions are non-negative. In fact, G1 has to be positive. And clearly, we can iterate all of them up to the beginning point, and we can get the following formula. And we have, and we would like to solve it. So to get the expected value of a function n at time, a function f at time n, we need to solve these products and these sums of products. Okay, and we have explicit values, for example, for average degree for function g1 in g2, similar for the fixed degree. Okay, so first, let's observe that both g1 and g2 are quotients of polynomials in T. So we can express G1 as a quotient of two polynomials in T, and similarly G2 can be expressed also as a quotient of two polynomials in T. Thus, if we want to solve this product, then we just have to notice that these polynomials we can split into certain monomials, and each monomial can be represented. So each product of the monomial can be represented as a quotient of two Euler gamma functions. So for W1 is responsible for this left part. So for gamma n plus rj divided by gamma n0 plus rj, and and similarly for W2. And here, what was left is to just peruse some old algebraic textbooks and find asymptotic properties of gamma function, especially if we divide for n going to infinity two gamma functions with n in it. then we can find that its asymptotics is proportional to n to the power of difference between these values with some smaller factor. Okay, so the first step is done. So we can already handle the first product, and the second we need somehow to get around sums of such products. With sums of such products, it's similar, only it requires us to also to present G2 as a quotient of some Euler gamma functions, which is fine because in fact, if we have any polynomial that it can be presented as such in this form, and then we approximate the sum by an integral. And in fact, whenever we approximate that, there is certain error, but this error is proportional to the values at the endpoints of the integral. So it is, I think if in our final analysis, it was bounded by a constant. And then again, we can use the tricks which were presented. It turns out that all the behavior depends on the values of the roots of both G1 and G2 functions. And in particular, it depends what are the, since we know that, for example, G1 can be presented as a quotient of two polynomials. One would be some like t squared plus 2p minus 1 times t minus 2r or something like that. That in fact the proper value which affects the most our rate of growth is the second term. So whenever we have, for example, here we have 2p minus 1, that we suppose that the rate of growth would be proportional to 2p minus 1. With some small deviations in case that the other terms might be more important. So for example, whenever p is less than 1/2, then there will be always present certain constant terms and they would dominate. And if p is equal to 1/2, then due to this integral, we have an integral of something which is proportional to 1/t. So we get logarithm. And similarly for vertices, we can find as well, and here for vertices S, which are at the beginning of the graph, so there are some constants, we can find that they either behave as proportional to logarithm or to t to the p. Okay. And this analysis can be performed even more thoroughly. So we can find, for example, explicit constants which are hidden under theta, and we can find these formulas for not only for S, which is constant, but for any values of S. And there are, if I remember correctly, 4 cases with different formulas. So eventually, it is all more or less in the largest case proportional to t over p. But with some differences in mostly in the leading constants. And there is additional question that can we perform this for example, with expected number of triangles or other subgraphs? And in fact, it should be doable. So we need only to find a respective recurrence which would compute, for example, the expected number of triangles depending on the other structures that existed at time t-1, and then we would be able to form a certain recurrence and solve it exactly the same way. Okay, but this is only the expected value, and this is only the stepping stone to theorems proving the behavior of the whole model. And for example, for large deviation, we have certain proofs that can show that if we try to get some bound on the expected value of the exponent of an average degree, then we arrive eventually at the formula that we have certain explicit functions h1 and h2, and we can bound it by a certain constant depending on the average degree of graph at time t0 and the product of exponents of function h2. In fact, whenever we have such bound, then we can use Chernow bound, which probably all of you know, and we can arrive at the following formula, which describes the relation between the probability of the value of d of gt exceeding some constant times, so some value times the average value, and we have we can bound it by an expression which has 3 parts. And the trick is that if we suitably bound each part, and actually the green part is constant whenever we whatever we put in place of lambda t0. The latter part, also, if we pick epsilon t, which is slowly going to 0, that it can also be bounded by a constant. And we know that by the same reasoning that in the first part, it is sufficient to take alpha, which would be proportional to logarithm square, to get that probability of degree exceeding some fixed constant times the average value times square root of logarithm of t is less or equal than probability proportional to, so this is less or equal than t to power of minus a. So formally it holds the converse event holds with high probability. So we know that average value times logarithm square serves as an upper bound with high probability. Okay, and we can do a similar reasoning for lower bound, which turns out to be in this case -3 minus some logarithm. So this is slightly worse bound. And we can do it exactly the same reasoning with the degree of vertex S. So both average degree and degree of a fixed vertex, of a fixed constant vertex, are concentrated around certain value. In this sense that whenever we go logarithm square up or logarithm cube plus something down, we go outside the region of high probability. Of course, the question is it the best bound possible, or whether the convergence, it can be proved that it converges to one true value. This is still open. Okay. So here we have these results that we have this behavior of a degree of a fixed vertex. Clearly, this gives us bound on maximum degree. Here we have degree of a lower bound of a degree of a fixed vertex. And here we have upper bound. And of course, lower bound on a degree of a fixed vertex give us a lower bound on maximum degree. Right. Right. So probably I wrote here in the other fashion, but the first theorem is also preserved whenever we put delta of gt instead of degree of t of s, but the second, unfortunately, not. So we have the lower bound, then we would like to have an upper bound. And there is a question whether we can prove something like the latter theorem. And in fact, we can. So what we did was to make stronger the lower bound for maximum degree, and we get slightly weaker, but all in all quite decent, because this is also t to the p times some polylog as an upper bound. And it should be on the right-hand side 1 minus OT of minus A. So the probability that we are between these two values is very large, not very small. Okay, so our strategy is to introduce sequences which are that we pick certain moments in time, t0, t1, up to certain tk, and we pick associated variable, it is the deterministic sequence xt. Next, we prove that for all early vertices that from 1 to t0, xt serves an upper bound of degree of s. Quite surely. Quite surely it's that it is the probability of converse event is below t to the minus a for any a. And of course, we would like, whenever we have proof for s less or equal to t0, then we would like to inductively prove it for t1, t2, and so on up to tk. Okay, and the similar goes for the lower bound. Only in the lower bound we do not have these formula that degree is less or equal than x, but rather we have degree which is greater or equal than x minus t0 plus 1. Okay, so here are the recursive formulas for both t and x. And since they are both deterministic, that for now we leave unspecified alpha, beta, I, and phi. And we would like to get their behavior depending on alpha and beta. Okay, so whenever we have phi that's that is slowly growing, so at least at logarithm square, but we suppose not too fast, and we have certain assumptions on alpha and beta, then we can prove that xt grows at least as fast as t to the p minus delta. And the proof goes by using simple approximations. So for example, if here we use the fact that we can 1 plus some small value to the power x can be bounded from above by this small value times this exponent plus 1, right? So so actually we bound this whole formula. Okay, and another, since we assume that this holds inductively, that we may prove the latter line, and it turns out that at each step xti plus 1 minus xti is somewhat greater than the respective difference between y's, and difference between y's is exactly the difference between ti plus 1 to p minus delta and ti to p minus delta. So of course the proof holds, and we have that. So from now we know that x is growing sufficiently fast, almost, with this small factor of delta, which we'd like to get rid of. Okay. And then we can use this lower bound to prove the upper bound. And to prove the upper bound that we have xt does not grow faster as t to the p logarithm t times some factor dependent on phi, but it is good because phi is polylogarithmic. So it has to be at least polylogarithmic, but eventually we want it to be polylogarithmic. And this proof goes along the same line. And this way we get what we want, that we have the gap between ti and ti plus 1 is quite small. And if phi is bounded by a polylog, then x is bounded by a polylog. T to the p times polylog. Okay. And then we have proof with very elaborate assumptions. But the trick is that it is just a Chernoff bound for degree of a fixed vertex. And it just says that whenever we increase the large increase in the degree of vertex in the interval of length h is very improbable. And now only trick is to get the constants properly valued, so we can fit a value within this interval. So this interval is non-empty. We can find a proper value, and we can get the proper phi, alpha, and beta I, so that all the assumptions are fulfilled. Okay. So then we know that this Chernoff bound implies that at each point ti, if the degree did not exceed x of ti, then it is very improbable that at time e plus 1, this is broken. And of course, it is obvious that at the starting point, we decide what are the degrees, and we let x of t0 be exactly that, so that it would be greater than any vertex at time 0. So it holds with certainty. Okay, so by simple summing argument, we know that the probability that degree of vertex S at time t does not exceed x of tk is very small. And it is very small, then clearly the union of such events is very small. Okay, now we use it to bound the the later vertices. So for later vertices, we know that for now we know that all early vertices have degrees which do not grow too fast, which grow as much as t to the p times polylog. And here we use induction in that sense that in each space between ti and ti plus 1, every vertex has to be a copy of some early vertex or a copy of some vertex within the same interval which was earlier. And we prove it one by one. If we take any single interval, TL plus 1, we can prove that its initial degree cannot be greater than 1 plus epsilon plus some linear function of xtl plus 1. But we assume that p is less than 1, epsilon can be arbitrarily small, and x is growing, so that actually these vertices cannot be with any noticeable probability, cannot be the maximum degrees, the vertices with maximum degree. And then we prove it one by one, vertices within one interval, and then interval by interval, we prove that that the starting vertex is small, and then the value of degree of this vertex at the end of its interval is also small. And then we can apply the generic Chernow bound, which was mentioned a few minutes ago. Okay. So all in all, we get that all vertices from the interval do not exceed t to the p polylog t with any decent probability. And with the lower bound, we proceed exactly the same, only we use different Chernow bound, right? So we use the same strategy, the same technique, only different values, and we have different intervals. And all in all, it's all the matter of technique to get this. And again, we have to pick proper phi alpha and beta I and all other parameters to get what we want. And eventually, we get at the same result, only that we have, this time we have the lower bound as a t to the power of p times some constant, which is strictly less than 1. Okay, so this is the end of this proof. And now with the latter part of my talk, so this power law phenomenon. And we go back to the pure duplication model. So let us suppose that we do not have any edges which are related to value of r. And we are interested in the behavior of the degree of the vertices, so the number of the degrees, number of vertices with degree k. And we are interested whether there is some scale field property, there is some power law or not. Formally, we can define a fraction of vertices with degree k as f of k, and it is asymptotic. So as number of vertices goes to infinity, then it is the expected number of vertices with degree exactly k. And previously, it was found that almost all vertices are isolated eventually in model with no r edges. So almost all values of f are 0, and the only non-zero value is for isolated vertices. And then that was tiny result whenever we have this pure duplication model with r equals 0 and 1 p. Then the number of vertices with degree 1 grows at least logarithmically. So its fraction is at least logarithm t over t. Okay. Then came Jordan, and he proved that this pure duplication model behaves in a certain range almost as power law. So he said, okay, let's cast aside the isolated vertices, and let's prove the theorem for p between 0 and e to the -1. And he proved that whenever we have some value which is solution of this equation, then whenever we are below it, this goes to 0. Whenever we are above it, this goes to infinity. Still, it is almost power law because it still does not prove that ak is proportional to k to the power of q. There can be certain polylogarithmic factors, or or even as long as they are not proportional to k, they can appear. And what he used, he basically discarded. So we can compute this at hand by averaging, but he proved one very important thing, that it is actually good to go with some vertex tracking approach. And it goes like that. Suppose that we pick a vertex uniformly at random, and then in case it was copied, we jump to its copy. Whenever it wasn't copied, we stay the same. So here it is assumed that V3 is a copy of V2. And we have, at each point, we have one vertex which is tracked, and we can get its degree, right? So we can have its degree. And it turns out that the behavior of such stochastic variable, which is described by this tracked vertex degree, can be described by a Markov chain. And one trick he made it into continuous time Markov chain. And we got this matrix. Of course, this matrix is changing over time. But one important thing that he got the quasi-stationary distribution of degrees. And one more thing that he noticed is that he turned it into a GF equation, right? So we have generating function A, and we have the following formula. And he proved from this, actually that the theorem that I've just shown. But what we did, we basically took his equation because it holds firm, and then so this is the solution. But the solution is not as important as it looks. The only thing is that this is the very large constant that describes the quotient of A of k divided by k to the power of beta. And the trick is that this is indeed asymptotically going to a constant as k goes to infinity. Okay. So the trick with, in fact, we performed some tests to find numerical values of these constants, and it turns out that indeed it breaks down whenever p goes to 1 over e at one side, at 0 on the other side. That both here it goes, so here it goes to infinity, here it goes to 0, and actually there's the value is undefined for 1 over e. Okay, what we did, we took Jordan's equation, we made a few substitutions, and we got the following equation with value of c. Okay, and we knew there are boundary conditions because, of course, since A is a probability distribution, it has to have certain boundary conditions. Then we wanted to use the trick, so the transform, which is called the Melon transform, and which is defined like here. The problem is that Melon transform requires us to have boundary conditions not at 1 and infinity, but at 0 and infinity. Okay, so we did the trick. Let's assume that we have the same function, only it is expressed in e, and it has different constant here, right? Because this is constant, so we can put any constant here, and thus we have this function. And let us assume that it has such boundary conditions that Melon transforms exists. Okay, so suppose we find this solution. Then to reverse it, it is sufficient to apply this linear transformation, right? So we can use this and we can obtain the solution for CW. And our proof began by actually by guessing. So from that, we knew by our rough computations that the solution should be like that. Okay, and there are two things that we want to prove. First, that it indeed has the reverse Melon, which gives us this equation. And second, which properties does it have? So if we look at this, function, then we note that there are this function has only 3 types of isolated poles. So only at certain points it is undefined, and where is it? It is undefined. From all negative integers, because gamma functions for non-positive integers is undefined. Okay. Then for all positive integers, because this quotient 1 over ds is undefined for them. And it turns out that since d of s it's this large product, then it has also every such expression has two roots. One root is equal to some natural number, and one is equal to some to the non-trivial solution of this equation plus some natural number. Okay. And the trick is that we can use it. Actually this function behaves very well because d of s is absolutely convergent. Then actually it decays as the real value. So as the imaginary value goes to plus and minus infinity, but it is sufficient to know that it's absolutely convergent. At least for real values, so for real parts of S being between -1 and 0. And next, what we show, we use the reverse Melon transform, and we show that indeed it is the case. So first, from the definition, we prove that it's straightforward that that many terms cancels out, and there is this recurrence. And we apply reverse Melon to obtain a formula for E of W.